Today we're going to be discussing electron configuration, a different way to do electron configuration that's even shorter than the method we learned in our last set of notes. If we look down at the bottom of this page, it's possible that your set of notes might say abbreviated electron configuration. Rather than rare gas configuration. It's known both ways. But what this does is it shows the structure of the electrons using the noble gases in brackets to represent a portion of that electron configuration. For instance, if we go to the periodic table and look for strontium, strontium is here in the periodic table. And strontium, as you can see, is in the 5s sublevel. That means its last electron, its last electron cloud is in the 5s sublevel. And if we wrote all of the electron configuration in order for strontium, we would write 1s, 2s, 2p, 3s, 3p, 4s, 4p, and then 5s. However, we're going to be able to shorten that considerably. We can take all of the first part of the electron configuration and we can simply put in brackets the noble gas closest to strontium without going over and substituting it for that portion. For instance, if we look over here, these are the elements that we're going to be able to put into brackets right here, these noble gases. And if you notice for strontium, the element, the noble gas that is closest to strontium without going over is krypton. So what we're going to be able to do is to write krypton in brackets, and I'm going to write it right here so that you can see it on the same page as the periodic chart. We're going to be able to write krypton in brackets, and it's going to take care of everything up to and including 4p. And all we have to do is write whatever comes after krypton. And all that we have after krypton is 5s. And since strontium is the second element in the 5s sublevel, all we need to put is a 2 here. So let's go back and do that on our notes. We have krypton in brackets. And we simply have the 5s2 after it, and that takes care of the rare gas electron configuration for strontium. If we still want to write the quantum number set, then again we need to pull off on a piece of scratch paper or something the orbital notation of just that last sublevel. And the last electron we put in was that down arrow. So our quantum number set for strontium is going to be 5. Remember that an S is designated as a 0. Since it's only got one blank, then we're going to be able to simply, that is the middle blank, so we're going to be able to label that as a 0 also. And since that's a down arrow, it's a -1/2 for the last part of it. So there is the abbreviated electron configuration for strontium. Iodine, if we look back at iodine on the periodic table, iodine is here. And remember, when we're writing the abbreviated electron configuration or the rare gas configuration, we want to find the noble gas closest to iodine without going over. Now, it looks like xenon would be the closest one, but xenon is after iodine, so we cannot use that one. So we must go once again back to krypton. So once again, we're going to be using krypton as our element in brackets, and all we have to write down is whatever comes after krypton. So I am going to write for iodine. I'm going to again do it on this page first so that you can follow along on the periodic table. That we would write krypton in brackets, and after krypton comes 5s. And after 5s, 4d. And after 4d comes 5p. Remember that all of the S's have 2 electrons, all of the D's have 10. And if we count over from where 5p starts, we see that iodine is in the 1, 2, 3, 4, 5th position, which indicates that there are 5 electrons in that 5p sublevel. So that's the abbreviated electron configuration for krypton. We can go back to the notes and write that in. We have krypton, 5s2, 4d10, 5p, 5. And again, somewhere on scratch paper or something, you can write down that 5p sublevel. Remember, a 5p sublevel has 3 orbitals. And those 5 electrons, according to Hund's rule, are all going to go in facing up, spinning up, if you will, for the first 3, and then it has to double up for the 4th and the 5th electron. Remind yourself that we're always going to be finding the last electron that we wrote in. We're going to be finding that particular quantum number set. So if I put my parentheses out here, I see that the first number, once again, is 5. Since this is a p sublevel, the second quantum number is going to be a 1. The third quantum number is going to be, since this is in the middle blank, it's going to be 0. And since it's a down arrow, -1/2. So that's the quantum number set and abbreviated or rare gas electron configuration for iodine. Tantalum, on the other hand, if we look up tantalum on the periodic chart, tantalum is right here. Once again, we're going to pick the noble gas closest to tantalum without going over. We can't choose radon. Radon is too big. It's bigger than tantalum, so we have to go back to xenon. So we're going to look at xenon as being our element in brackets. And everything after xenon, we need to write down. So if we put xenon in brackets, the next thing we come to is our 6s. After 6s, please, please, please don't forget that you need to draw that early line, one element is a little bit short, and remind yourself that the 6s goes down to 4f before it comes back and picks up 5d, and that the 7s would go down to the 5f before coming back up and picking up 6d. So after 6s, we're going to have 4f, and then our 5d. S's have 2, F's, remember, have 14, and our D sublevel, since tantalum is 1, 2, 3rd in that sublevel, we'll have 3 electrons in that 5D. So again, we'll go back to the notes and put that in. We have Xe in brackets this time, 6s2, 4f14, 5d3. Pull out the 5d. Write in the 5 orbitals for a d orbital, or for a d sublevel. And we've got 1, 2, 3 electrons. Notice that, once again, that last electron is the one we're going to find a quantum number set for. So in parentheses, a 5 once again. This time we're dealing with a D, so we're going to have a 2 for our second quantum number. Once again, we're in the middle blank, so 0 for our third quantum number, and since it's an up arrow, plus 1/2 for our fourth quantum number. We also want to be able to look for an element in a specific position. For instance, if I asked you what the 3d5 element was, going back to the periodic table, we see that if we're in the 3d sublevel, 1, 2, 3, 4, 5. Manganese is in that 3D5 position, so we're going to put M in for manganese. 4P3 going over to 4P in the 1, 2, 3 position. You see that we have arsenic. I'd like you to pause it really quickly and see if you can do 5F10 and 2S1 yourself really quick. And hopefully you did that. 5F10, 5F's down here in the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th position, we see that we have Einsteinium, ES. Hopefully that's what you got. And for 2S1, up here at the 2S sublevel in the first position, we have lithium. So just working backwards a little for that. The last thing that I want to talk about today, if you have some additional notes on here, we really won't be covering those this year, but there are exceptions to the rule. AP's changing a little bit on how it's going to deal with exceptions to the rule, but we're going to go ahead and look at least the D4 and D9 elements that occur and what happens often with those. When we have D elements, there's a lower energy situation that occurs when the final sublevel in the atom, that D sublevel, is filled or half filled with electrons. So what happens is that many times the D4 and D9 elements will borrow an electron from the previous S sublevel. For instance, if we were to draw the electron configuration of chromium, looking back at where chromium is on the periodic table right here, we would draw, first of all, the closest noble gas, which is argon, Ar. We would have argon in parentheses, and we would have 4s2, 3d4. But if you look at that 4s2 and 3d4 in orbital notation, you'll see that it looks like this: 4s2, 3d4, and it is a lower energy situation for that 3d orbital, or those 3d orbitals, to be half filled. So what happens is this s electron will be popped up and taken into that final 3d orbital, and what we end up with then is 4s1, 3d5. That's what we're going to see. So again, this one gets popped up, it moves out of this position and into this position, and we're going to change this then to read 4s1, 3d5. Again, this happens on D4s and D9s. When you see or write down a D4 or a D9 in your electron configuration, bells should start going off in your head, and you should be thinking, no, it's not going to do that, it's going to borrow one. Take silver, for instance. If we look back at silver's position, silver's right here. Silver, we're going to write krypton in brackets. It's the closest noble gas without going over silver. So we're going to write krypton in brackets, and we're going to write in the 5s and the 4d. And if you'll look back, you'll see that it should be 5s2 and 4d9 when you write it down at the beginning. But at this point, bells should be going off in your head, because that 4d is almost full. If you write the orbital notation for it again, it's going to look like this: 5s, excuse me, I wrote a 2 instead of an s, 5s with 2 electrons, and the 4d with 9. And again, what's going to happen is that electron, one of the electrons in the S, is going to be popped out and put into the d orbital so that it fills it up. It's just a lower energy situation. So this is going to change to a 5s1 4d10. Now make sure when you do that that you change the quantum number set, because the quantum number set, the last electron we write down now, is right here for chromium and right here for silver. So make sure you do this orbital notation first and change it before you do the quantum number set, because you'll be off on that third quantum number if you don't. So looking at chromium, it would be a 3, 2, and since this is -1, -2 opposite number line order, this would be a -2 and a, since it's an up arrow, +1/2. And after the change for silver, it would be a 4, 2, and since this is once again in the -2 position, this time it's a -1/2 since it's a down arrow.